Uh, Good morning, everyone. So, as this is almost the time, I will start my presentation for today. So, for today paper seminar, the title is MIXLORA, Enhanced Large Language Models, Fine-Tuning with LoRa-Based Mixture of Experts. Following my previous presentation about the integration of mixture of expert with LoRa, this paper is the most recent released paper in this direction of research. The outlines of my presentation will be as follows. And let us start from the abstract and the motivation behind this paper. As we already know, like fine-tuning large language models, and especially like instruction fine-tuning large language model, achieve like impressive performance in different downstream NLP tasks. And as we increase the number of the parameters of the language model, its capability for close generalization improve. So when we have like a vast amount of number of parameters, we have now to trade between the computational resources and the computational cost of the full fine-tuning and the performance we want on the downstream NLP tasks. So here where is PEFT being introduced to reduce the number of the parameter being tuned during the fine-tuning. And the most popular method is the low-rank adapter method, which effectively reduce the GPU memory constraints for compared to the full fine-tuning method, and at the same time has like comparable performance to the full fine-tuning. But this is for single task approach, but when we apply it for multitask scenarios, its performance falls short. So there is some mixture of expert-based large language model like MIXLORA being released recently, like this year, and some like famous LLMs like GPT-4 being like following the same architecture, which is 8 by 7 billion mixture. But applying this mixture of expert-based large language model for multitask scenarios like have excellent performance, and comparing like to its performance, which is comparable to GPT-4 and GPT 3.5. It is really like reduce the number of parameters being needed, like while inference using Mixtral, we just need like around 13 billion parameter per token. But still, it is like very challenging to apply to use this model like for limited resources consumers, like with, for example, 24 GPU memory. So how they can get the two benefits from two different methods. That is why they apply, they introduce MIXLORA. So it will be a resource efficient and at the same time mixture of expert model, following the same way of integrating LoRa MOI method. They integrate multiple LoRa-based expert, but just in the feed-forward module. And follow as the same as LoRa, they keep the frozen pre-trained model, and they use it sparsely, so they just use select the top K experts, and as I said, the MOE LoRa is being just added to the feed-forward network module, but they add one LoRa module in the attention layer to improve the performance. Uh, Additionally, following the other papers on LoRa MOE, they introduce auxiliary load balance to balance the address of the router for of the tokens for each expert. Okay, let us go through the brief introduction. Um, as I said, fifth method, and specifically LoRa, uh, uh, give an excellent performance for single task fine-tuning and a comparable performance to the full fine-tuning, but it is still like for short for the multitask scenarios. So there is some research trying to improve the LoRa method, like LoRa Plus or DORA, decomposed low rank adapter method. And both of them trying to improve the way the parameter being updating in LoRa during the fine tuning. Other two methods being trying to improve the cross generalization capability, like for multitask learning by adding like task specific modules, either like adapter fusion or in LoRa Hub like task specific adapter also. But both or all this method still have limits applicability because of the limited numbers of LoRa being updated during the fine tuning. Comparing like if, for example, we have a 7 billion model, the number of LoRa parameters compared to the total large language model could be like 1 or 2% or 3% compared to the full model parameters. And recently, the most uh, approach gaining attention in this scope is combining LoRa with MOE, which a resource saving, combining the resource saving feature of LoRa with the multitask capability of MOE. As we can see, this table, it's almost like summarize recent announced paper, not all of them, but most of them, being announced from the end of 2023 to April 2024 is MIXLORA. And we can say all this method almost following the same idea of integrating LoRa with MOE, but with different configuration and application. Some of them used it for like solving specific issues, like for example the word knowledge forgetting, that the model start to forget the knowledge that gained during the pre-train stage when fine-tuning on like huge downstream task dataset. Another problem also is lifelong learning, how we can give the model the knowledge like continuously. Some of them focusing on the multitask learning as medical multitask learning and MOE mixture of LoRa's multitask learning also. But the general idea of all other methods different from MIXLORA. If we like see like here's for some other details. Either they have this is vanilla LoRa, which just adding plugging or fusing the low rank adapter with the attention module, and this is what all the others method being do. They treating all the experts or the LoRa modules as one LoRa, like as one big LoRa module. having like multiple modules and then routing or doing the weighted sum and adding the final output to the attention module output. But what is different here in MIXLORA, instead of acting as each expert, all the experts as one big LoRa module as a single fine-tuning way, they trying to follow the idea that being applied in the mixtural model, which having a shared FFM module. So we shared this FFM module between each LoRa experts and calculated the output of each FFM module like as follows, and then applying the routed sum or the weighted sum uh, as follows. So yeah. And instead of, as I said, it is just being applied for the FFN module. And for the self-attention module, instead of applying the MOE LoRa, they just plug one attention layer as follows. And as we can see, by doing this, they add more computational like cost to the total MOE LoRa, because now we have to calculate the output of each shared FFN plugged with or fused with one LoRa adapter. So if we have, for example, N experts, now the computational cost for just this one FFN module will be multiplied by N times. So to reduce this amount of computational cost, they improve a high performance framework in this paper, as we will see. So let us have a like brief introduce to the related works. As we know, in mixture of expert, we have multiple specialized networks, and they take this idea and apply it to the transformer blocks by using like sparsely activated expert, which being activated by the gate mechanism or the router. There is a different way this architecture being introduced to the transformer blocks. For example, in Lava MOELE, which is a multimodal for multimodal approach, they try like to route the token to just to domain specific based on the token, so they can mitigate like the data conflicts being assigned to experts that is not on the same domain. Here, like in MOERLAL, they, as it was being here, yeah, it's being applied not for multitask learning, but instead to add the knowledge of new domain or new tasks. So now we will have efficient lifelong learning. In LoRa MOE, they try to elevate the word knowledge forgetting. And in this paper, PESE, they try instead like going from the dense model to sparse model. So when we have a new tokens input, instead of use the whole model, now we just use part of it as the expert being activated by the router. And this will end up with reduced computational costs, which is same idea of the, almost the mixtural, which is MOE based pre-trained large language model. Also, we have MOE LoRa, which is different from others because they try to assign different number of experts for each transformer layer. And finally, we have MOCLE, which have clusters or like domains or being acting as clusters, and for each uh, instruction cluster, they activate the task customized parameters, which is the same as the hypernetwork idea. So based on the cluster that is being belong to, then we will use the parameters of the adapter to be activated. Next, we will just give a brief overview of LoRa and MOE because like we already like covered in the previous presentation. So as we know, in LoRa, we just tune the adapter parameter instead of updating or fine-tuning the original model adapter weights. And each LoRa block consists of two low-rank matrices, A and B. And for each LoRa adapter, we have the rank or the hidden dimension of LoRa as follow, and then the update of the weight will be this is frozen and just updating the PA matrices. For the mixture of experts, each MOE layer will be consist of n experts and being weighted sum using the router. So the output of the MOE layer will be the weight of the router multiplied by the output of the expert. Yeah, exactly. That is all. So now let us see the architecture of MIXLORA. So we can see the main two parts of MIXLORA is the MOE block, which is a transformer block being augmented or being shared with LoRa's, and the FFN. And then the top K router being assigned based on different tasks we have. So let us assume that we have an input text from S, and like for the vanilla transformer block as follow. We have the attention part and we have the FFN module. So assumes that we have H I of L, which is output of the I token for the else layer. So the um, so the output of the attention module will be as follows. Will be like the linear norm of the output of the previous layer. Applies a multi self-head attention layer, and with the residual. Then we pass it to the linear FFN linear module, following the same way. Linear normalization, applying the FFN with the residual. So how is this being modified in MIXLORA? So in MIXLORA, the vanilla transformer block will be modified as follows. They add one LoRa module in the attention layer, which we will discuss later. And the MIXLORA or the MOE layer will be added in the FFN. And as we explained previously, instead of being plugged with, it will be fused with. So we using this shared FFN, each expert will get being calculated as a single LoRa, and based on the router weights, then which expert being assigned will be activated, and then we have the weighted sum as the end. So going from here, this will be changed to the MIXLORA layer uh, uh, of like the linear norm of the attention layer output and with the plus the residual. And for MIXLORA will be the weighted sum of each um, expert. And the difference will be that instead just of have the output of the expert, it will be the shared FFN and the plus the expert, the LoRa modules, which, as I said, is same as we have one single LoRa module output. Um, so as I said, we have the router that based on the hidden state of the input, it assigns different tokens to different experts and just keep the top two experts. And same as other MOE LoRa approaches, they trying to solve the problem of the unbalanced load expert because the router layer tends to choose the same expert again and again. So for example, like if expert 3 being assigned like for so most of the time, it continuously choose the same expert, while some other expert being ignored or the uh, contribution being imbalanced. So to mitigate this, they introduce this auxiliary loss, which being as follows, like this is a coefficient to control the contribution of the auxiliary loss to the total fine-tuning loss, and is the number of the total experts. And then we have this which calculates the imbalance of the allocation of the router. We have the Fi is a fraction of the tokens being dispatched to like expert I. Rx is the weight of the router for expert I. And then we have the Ti, which is a fraction of the router probability allocated to expert I. T is the number of the token of in each patch, P, and using this um, auxiliary loss being added to the total loss, it like balance the assign of the router to of the tokens to the experts. Okay. Then going to this part, when LoRa modules being added to the attention layer. So usually like when we do the single fine tuning, either we add the LoRa modules in the attention layer or the FFN layer or module. But and like it is like as like a lot of research shows that adding LoRa modules to the attention layer have significant impact on the final fine-tune model, more compared to the FFN. So that is why they add one LoRa module to the attention layer, and as we can see, it will be like trainable and plus the experts weights. So it will be like fine-tuned during the training these parameters. And their experimental result shows that instead of just adding this mixed LoRa layer, adding this LoRa module to the attention layer has achieved superior average scores compared to only using the FFN module. So how they, as I mentioned before, because the computational complexity improve because of the shared FFN, they introduce a high performance framework to optimize it. So uh, as we can see, depend on the number of the experts we have, the computational complexity increase. And especially when we have like long sequence inputs, the impact of this configuration will be like noticed. So how they can solve it? Um, they try like to analyze how they can solve it, and they focus on FFN module taking, for example, Llama 7B, Llama 27B billion model. So in um, Llama 27 uh, Llama 27 billion models, they have the FFN as follows, and they have three linear modules, like the down projections, up projection, and the gate projection, which is W1, W3, and W2. And the output will be calculated as follows. But to reduce the number of the computational being applied, like for each expert, as I said, it will be multiplied by n, the number of experts. They uh, uh, as we can see here, the um, input being like sliced and assigned to different experts. And we can see this part as this part is independently of the expert uh, uh, operation. So they they like put it outside the expert shared area, and just like from the calculated it first using the input hidden state, then shared it between the all experts. This part cannot be shared because it's output being depending on the uh, these two parts. So um, by like processing the input like directly first and shared the output over all the expert, they reduce 1/3 of the computational complexity, 30% reduction in the token computational latency, and at the same time, it maintains the same model performance of MIXLORA. Other thing they do for optimizing the inference, for each single patch, they try to like pack multitask input. Like for example, if we have like 8 tasks or 8 experts, each single patch should contain at least one input related to each task, and then we by applying this parallel processing, uh, they reduce or they achieve a reduction about 45% in the big GPU memory usage per model, uh, while maintains the same token computational latency here during the training. So this is the experimental setup. They use a question answer task, which is like either yes or no question or multi-choice questions, and classification task, science completion task, and fill in blank tasks. All these tasks being labeled by the correct answers, and as follows, they use the accuracy as the evaluation matrices. The baselines for this experiment will be like Llama 2 7 billion, 13 billion, and Gamma 2 billion, and Llama 3 8 billion. The result or the experimental result will be based on LoRa, DORA, uh, which is a decomposed version of LoRa, and MIXLORA, MIXDORA. The number of the specification of the hidden adapters like layer. The rank is based on the total number of parameter, like almost. So they put it 80 and 60, while we have 8 experts to maintain the same number of the parameters almost during the evaluation. And for the LoRa and DORA, they activated all like the attention layers and the FFN layers. So first, let us see the single task fine tuning. So uh, almost like for all the average DORA superpass LoRa average. And while like MIXLORA and MIXLORA like maintain commendable performance for the single task scenario. And as we almost like, oh, sorry, although like MIXLORA or MIXDORA here like outperform MIXLORA on all the average matrices, but it is not always that for single task evaluation. Sometimes MIXLORA outperform MIXDORA, as we can see. So going from the single task evaluation to multitask in fine-tuning, they just focus on these 5 datasets and mix it together and do the multitask fine-tuning. So as we can see, the average evaluation of LoRa and DORA shows like a degradation in the average. And for mixed LoRa and mixed DORA, they almost like shows the lowest performance degradation, or it is not a degradation here, like almost maintains the same performance, which is strong generalization ability. It shows like the strong generalization ability. And at the same time, we can see it as they mitigate the knowledge forgetting for the multitask learning better than the LoRa and DORA. So, in conclusion, in mixed LoRa, they integrate I've used multiple LoRa-based expert with a shared FFN block, and which being different from other like MOE LoRa integration approach. And to enhance the fine tuning, they incorporate one LoRa adapter in the self-attention module, and introduce the low balance, the auxiliary loss to the total loss to balance the token distribution across the experts. And finally, to reduce the overall like complexity, computational complexities, they introduce their high performance framework to share the like output of the FFN weights among the experts, which save around 30% and 40% in the GPU memory usage during training and inference. And yeah, so far this is the end of my presentation. I would like to answer if anyone has a question.
But
Yes, Professor.
yeah, page 17. In LoRa and DORA model, what does it mean to have multitask running?
So just like mix the data set, this data set be mixed in one data set and do a single fine tuning.
Uh,
Uh,
Yeah. Mhm. Mhm. Simply uh, all data set combined.
Exactly, yes.
Yeah. Uh, yeah. Another question. Compared to single aura model, uh, multiple aura model are expected to not always show superior running results. Uh, we will list enough fine-tuning data to run multiple aura. Uh, however, in the real problems we are trying to solve, such data is often not available. Uh, how do we collect enough data?
Mm,
Uh, in the papers, such data are given, but however, in the real problem, we are collect fine-tuning data.
yes.
Yeah.
Um, I think like as we creating or generating the data set by ourselves, creating enough data sets that can optimize like single fine-tune results could optimize the same data set, like could optimize multitask fine-tuning.
Mhm.
But they don't like discuss the amount of data set being needed for like single task or multitasks. Uh, they don't focus on analyzing it.
Oh, yeah. I think we must think about that uh, data data set collection. Yeah.
Yeah, yeah.
Yeah.
Okay. I put my mind.
Yeah. Yeah. Okay. Yeah.
Uh, anyone else has any question? Okay, then if there is no more questions, I will end up my presentation for today.
감사합니다.